All right, so this is the first video in the series of videos where I'll do all of the practice exam 3 problems. So let's just start with number 1, part 1. So we have a sequence where the terms are natural log of n divided by square root of n. We want to know the limit of this sequence if it has one. What we'll do first off is just see if we can take the limit of the numerator and divide it by the limit of the denominator. In some sense, that's always what we want to start by trying to do. But pretty quickly, you'll see that the natural log of n as n goes to infinity also goes to infinity, and square root of n goes to infinity as n goes to infinity. So it turns out that this is an indeterminate form of the type infinity over infinity. And so we're going to have to do something a little more clever than just plugging limit into the numerator and denominator. So since we have an indeterminate form, we can use L'Hopital's rule, and it turns out that that is very helpful in this situation. And so before I do that, I'm just going to rewrite the terms. Natural log of n I'll leave, and square root of n I'm going to write as n to the power 1/2. It just makes it easier to differentiate. And so now basically what I'm thinking is I have two functions, one being natural log of x in the numerator, other being x to the power 1/2 in the denominator. And essentially the deal is if the limit as x goes to infinity of this exists, then it equals the limit of this as n goes to infinity, which seems pretty clear. The only difference being that x is a continuous variable here, so it can be any real number, and n is only a positive integer. So either way, we're going to use L'Hopital's rule. We already know that this is an indeterminate form, so I would like to just take the derivative of the numerator and denominator, and so that's what I'm going to do here. So I differentiate natural log, I get 1 over x. I differentiate x to the 1/2, and I get 1/2 x to the minus 1/2. And so now I'll just need to rearrange these terms and see if I can say anything about them. So it turns out that I have actually 1 power of x in the denominator. This x to the minus 1/2 in the denominator moves up to the numerator as x to the 1/2. And so this turns out to be 2. I have x to the 1/2 in the numerator. I have x in the denominator. And so ultimately, I'll be able to write this as 2 over x to the power 1/2. And so now the question is, what is the limit as x goes to positive infinity of 2 over x to the power 1/2? But of course, this is essentially just x to a negative power, and so we see that this goes to 0. So what I'm saying here is that the limit of the terms a n as n goes to infinity, right, limited natural log over n to the power 1/2, n goes to infinity. This is equal to the limit as x goes to plus infinity of 2 over x to the power 1/2, and this was by L'Hopital's rule. And what we just said is that this is equal to 0. So what we found out is that this sequence is convergent, certainly, and even more so, the limit is equal to 0. Okay, so that's the first part of the first problem. And so now we'll move on to the second part of the first problem. And so in the second part, we have terms of a sequence, and the terms are alternating because we have this minus 1 to the power n. So for even values of n, this minus 1 to an even power, well, it just turns into 1. For odd powers of n, this minus 1 to an odd power will turn into negative 1. So it'll depend on if n is even or odd, and that'll determine the sign of each one of these terms. Okay, and so what we're going to do is look at the absolute value of the terms. Reason being, because if the absolute value doesn't go to 0, then we'll be able to find two subsequences that go to two different values. And so what that's going to mean for this sequence without absolute values is that the limit will not exist. And so those two subsequences will come from when n is an even integer and from when n is an odd integer. Those are the two subsequences. So either way, we're going to evaluate the limit of the absolute value. Basically, if it's not 0, well then the limit of the sequence itself cannot exist. So to do that, we're going to divide by n in the numerator and in the denominator, because of course we see that as n goes to infinity, both the numerator and denominator blow up. I don't care to use L'Hopital's rule here because I can get away with this algebraic manipulation. And so this turns out to be 1 over 1 plus 1 over square root of n. Of course, square root of n divided by n is 1 over square root of n, so hopefully that's not too difficult to see. And so then when I take the limit as n goes to infinity of the absolute value of the ANs, right, I have the limit as n goes to infinity of 1 over 1 plus 1 over square root of n. We know 1 over square root of n, that's going to go to 0 because it's n to a negative power, essentially. And then this limit will be 1. This limit is not 0, right? So we do have, for when n is even, if I just restrict my attention to even values of n, then what we're seeing is that subsequence restricted to even values will tend to 1. The subsequence with odd values, remember we have that -1 appearing in front of all of those terms, will tend to -1. And so what that's going to imply about the sequence is that the limit will not exist, right? And so again, the reason that this is the case is because if we take values of an for even n and kind of look at this limit as n goes to infinity and only restricting our attention to even values of n, this limit will go to 1. That's the same as the absolute value, because for even values of n, the -1 is gone. However, for odd values of n, we have that -1 there, and we know an absolute value, it goes to 1, so this limit will actually be -1, and here we're at odds with a -1 and a +1, so the limit of the sequence does not exist. So that concludes the first question on the practice exam, and so I'll start with the rest of the questions in the next video.